Right, you don't need anything pulled up here, right?
Nope.
Okay.
All right. Everything good to go?
Yes, sorry.
Okay, thank you all so much for being here. Really exciting to have you all out. We're so grateful to be having our lecture series back. My name is Amanda. You've gotten a lot of emails from me. I'm a lecturer in the department, and I'm also the outreach coordinator. So I'm especially grateful and excited to be here with you all today. I'll let you know what's going to happen today. We'll start with some trivia, so see what your prior knowledge is. And then we'll go over some announcements, so some things to look forward to in the summer. Then we'll hear our talk from our fantastic speaker, Shifra. And then we'll do a Q&A and some raffles, so make sure you stay at least until the raffle. And then we're still TBD on stargazing. There are lots of clouds, but they are moving, and behind those clouds are lots of clear patches of sky. So we'll let you all know after the Q&A if we're going to be observing outside or not. So cross your fingers that the clouds clear. So let's start with some trivia. So question 1, we're going to have 5 questions. The first, which of these objects is the most dense? So how this is going to work is I'm going to let you all think about it. And then I'm going to say 1, 2, 3, vote. And you're going to hold up 1 finger for A, 2 for B, 3 for C, 4 for D. Okay, so I'm going to let you think about it. And then I'll say 1, 2, 3, vote. All right, if we were in my class, I'd say talk to somebody around you, convince them that you are right, but I won't force you all to do that today. And the most dense object is a black hole, the most dense objects in our universe. Question 2. All right. What will happen to our sun after it dies? So this will be in billions of years. We don't need to worry about it. Don't let that add to your existential crisis. But it will one day run out of energy and die. Will it become a black hole, a white dwarf, a neutron star, or nothing? Time to think about it. People are already thought about it. 3, 2, 1, votes. All right, I see lots of confidence here. And the answer is, white dwarf, B. It is, in fact, a white dwarf. We know that for sure, despite the confidence of where that box is placed. But our sun is not a very exciting star. It's not very massive, which means it will have a peaceful death and be a fairly peaceful object. But that's good for us, because if our sun is not very exciting, it means that Earth is not bombarded with as much radiation or high energy as it could be. So maybe that's why we have life on Earth. Question 3. Oh, no. All right. We'll do the best we can. Type 1a supernovae are extremely bright explosions occurring in binary systems with at least one white dwarf. So these are when there's a white dwarf and a companion star, and it causes an explosion called a supernova type 1a. These are very bright. How many times brighter than our sun is this kind of supernova? So your choices are 500 times brighter, 5 billion times brighter, 5 times 10 to the 20 times brighter, or 5 times 10 to the 100 times brighter. All right. Okay, 3, 2, 1, votes. There was a little more discussion, but I still see some very confidently held hands. Who knows where the box is going to land this time? All right, but it is B. So about 5 billion times brighter. So if there's a supernova that happens, we can see it in our day sky if it is visible in the northern hemisphere. All right, question 4. What is the largest number of stars observed in a single system? So our solar system has one star, that's the sun, but that doesn't mean that all solar systems in the universe have to be like ours. So how many have we discovered? Got some discussion? Some debate? All right, 3, 2, 1, vote. All right, I'm seeing a good variety of answers here. I love that. I did not know this one myself. It is 7. So you can imagine that it would be maybe much harder to look at the sky and have an idea of what time of day it is. If there are 7 stars in the sky, you have to know where their positions are in order to know what time it is. So we have it much simpler on Earth. Okay, this is our final question. So give it all you've got. What is the name of the event where 2 neutron stars merge, resulting in so-called R process elements like plutonium and uranium? Is it a gamma ray burst, a fast radio burst, a kilonova, or a tidal disruption event? The questions got harder. All right, 3, 2, 1, vote. Very fun when we have a variety of answers. This one is a kilonova, not a tidal disruption event, a kilonova. And I will just take a moment to brag. I have nothing to do with the kilonova, but where I got my PhD, UC Santa Cruz, a team of astronomers were the first to observe a kilonova in 2017. So this is a fairly recent observational discovery. So very exciting. All right, thank you all for participating in trivia. I hope you learned some. Yes, round of applause for you all. And you'll learn even more after our talk. But first, some announcements. We're very excited to say that we're going to continue our lecture series through the summer. The exact dates are a little TBD because we have to book classrooms and they aren't available yet. But we are going to have one in June, July, and August. We have an amazing panel of speakers lined up. I want to highlight the July one we're going to do on a Saturday afternoon so that we can pair it with solar observing. So you'll learn about the sun, and then you can very safely, with special technology, look at the sun. So instead of doing evening observing, we'll do solar observing. Our other announcements is we're pairing with the New York Library Systems and the Queen Public Library System to bring some astronomy activities targeted to kids to local branches. So make sure that you're looking for that if you're interested, the libraries, and we will advertise for it. So we have our events calendar shown on this slide. All right, and with that, we bring us to the main event where we will hear from Shifra Mandel. Shifra is a graduate student in the department, and I will let her introduce herself.
Thank you. So as Amanda said, oh, yes, is that? All right, can everyone hear me now? Wonderful. All right, thanks all for being here today. As Amanda said, my name is Shifra Mandel. I'm a PhD student here at Columbia in the Department of Astronomy and Astrophysics. And I will be talking about dead stars today. And odds are that if you're here today, you're probably interested in black holes. What is a black hole? It's the most popular kind of dead star, and it's pictured here on the screen. A black hole is a kink in space-time. It has a singularity at its center. It's so massive and so incredibly dense, the densest object in our universe, so dense that space-time itself is distorted and it just folds in on itself. If a human were to approach the event horizon of a black hole, they'd basically be spaghettified. That's because the gravitational forces are so incredibly strong, but they also vary significantly over very short distances. And so the force on the legs, if we're assuming that this hypothetical person is going in legs first, would be so much stronger than the force on the upper body that they would essentially turn into a bloody noodle. So highly not recommended. However, in case you're concerned, I don't want you to have any nightmares. I just want to reassure you that this kind of really extreme space-time distortion only happens really close to a black hole. So for example, I'm just going to rescale this here. If the sun were to suddenly turn into a black hole, which don't worry, it won't, the Earth would then just continue on its current orbit, because at 93 million miles away from the sun, even if the sun was a black hole, it's far enough that the gravitational distortions would be basically the same to what the sun currently exerts without being a black hole. So we would not be killed by getting sucked into the black hole's event horizon. We would be killed by the lack of warmth and sunlight, which we do need to survive, but the black hole's gravity would not be a problem for us. So no sunlight, like I said, because famously, the gravitational pull of a black hole is so very strong that not even light can escape it. Hence the name black hole. And because by the laws of Einstein's special relativity, nothing can travel faster than the speed of light, this means that nothing is capable of escaping a black hole. In a certain sense, as paradoxical as it sounds, considering how powerful they are, black holes are very straightforward objects. And this is what's known as the no-here theorem. Because no information can reach us from beyond the event horizon, we don't have to worry about a lot of the details of what's happening on the inside of the event horizon. For example, what's the composition of the black hole? What is it made of? It actually doesn't matter for us when we're studying a black hole, because there are only 3 properties of a black hole that completely describe it. So the first one is mass, and the gravitational force of the black hole will depend, of course, on its mass. The more massive it is, the stronger the force, but also the more massive it is, the larger the event horizon, which is the threshold of no return where you can't get back. So for example, if you approached a supermassive black hole, you would not be spaghettified until after you pass through the event horizon, because the event horizon is so far away from the singularity that those really crazy tidal forces don't come into play until after you reach that point. But, you know, approaching a supermassive black hole, still not recommended, BT dubs. The second property of a black hole is the spin. So pretty much all celestial objects spin. Stars, planets, galaxies, they all spin, and black holes are no exception. They spin as well. So that's the other property of a black hole that we can measure. And then the third property is its electric charge. However, we can generally assume that the electric charge of a black hole is neutral. Black holes may have some electric charge when they're first formed, but they lose any electric charge to the surrounding matter very quickly. So this leaves us with just 2 heres, or 2 properties that matter when measuring a black hole, the mass and the spin. How do black holes come to exist? So to answer that question, we're going to take a step back. There are 4 distinct types of black holes that are very different from each other. They each have their unique properties and formation mechanisms. And the first kind is the supermassive black hole. All galaxies have one. Our own Sagittarius A star, which is the supermassive black hole at the center of our Milky Way galaxy, is pictured here on the right from the Event Horizon Telescope image. That has a mass that's equivalent to more than 4 million suns combined. And the other black hole that we have a picture of is from the even more massive galaxy M87. And because the galaxy is more massive, the supermassive black hole at the center is also more massive. Actually has a mass of over 6.5 billion suns. Now, the second type of black hole is an intermediate mass black hole, also pictured here. Not quite as massive as their supermassive cousins, but pretty formidable nonetheless. And then the third kind is called a stellar mass black hole. And it can be anywhere between a few times the mass of our sun to dozens of solar masses. And this is the kind that I'm going to focus on in this talk. So stellar mass black holes are the remnants of massive stars that exploded in a supernova, like the one shown in the image here, which happened in 1987. So you can see the image on the left is before the supernova eruption, and on the right, you see this really bright source in the lower right corner. That is the supernova. So those are the before and after pictures. So finally, there's a fourth type of black hole. That's the primordial black hole. And hypothetically, these are tiny black holes that may have formed in the very early universe, shortly after the Big Bang. And they haven't been observed, but we don't yet have the capabilities actually to detect their signals. But we're working on that, so stay tuned. But they could be all around us. In fact, there might be one in the room here with us right now. So back to our question, how are black holes formed? The short answer is they're formed from the remnant of a massive star that died and then collapsed in on itself. So like most of the matter in the universe, stars are made primarily out of hydrogen. And stars fuse hydrogen into helium in their cores. That is what makes a star a star. So there's a nuclear fusion factory at the center of the star that's powering it. And a lot of that energy is converted into radiation that streams out from the surface, which is what makes stars so bright. This image on the screen shows the star that is closest to Earth, also known as the sun. Every star starts off the same way. First, a cloud of gas and dust contracts into something called a protostar. Then, if the conditions are right, meaning the temperature and the density and the pressure have just the right balance, the core will ignite and hydrogen atoms will start fusing into helium atoms. And when this nuclear fusion process begins, that is when a star is properly called a star. All stars spend most of their lifetimes fusing hydrogen into helium in their cores, but different stars can undergo very different end stages once they run out of hydrogen, as this diagram illustrates. So you have a star like the sun all the way on the bottom. Once it runs out of hydrogen in the core, it's going to turn into a red giant, then eventually a planetary nebulae, and a white dwarf is going to be all that's left. If you have a more massive star, then you might get a type 2 supernova, not to be confused with a type 1a supernova that Amanda told us about earlier. And that might produce a black hole or a neutron star. So another thing that all stars have in common is that while they are alive, meaning while the nuclear fusion is ongoing in their core, the pressure released by the fusion process actually keeps the star stable because it balances out the gravitational force of the star that's pulling inwards towards the center. And that is how a star is kept in equilibrium. The gravity wants to collapse the star towards the center, and the pressure from the gas and radiation pushes outwards, and these two balance each other out perfectly. But once the star runs out of fuel, the nuclear burning ends, and now the gas pressure and the radiation is no longer available to fight against gravity. So what happens then? The star begins to contract from the immense gravitational pressure. And, oops, here we go, sorry. So depending on the mass of the star, there may be a massive explosion or a type 2 supernova. This happens for, very, very massive stars that are about 10 times the mass of our sun or bigger. That will not happen to our sun, as Amanda already mentioned. Supernova is a very rare event because compared to sun-like stars, those really, really massive stars are very rare. The more massive, the more rare it is. So when you get to a star that's 10 times as massive as our sun, there just aren't many of those babies around. So the picture on the right here is of the Crab Nebula, which is the remnant of a really massive star that exploded thousands of years ago in our galaxy. The light from this supernova was observed in the year 1054. And this image shows what the afterglow looks like today, almost 1,000 years after the explosion was detected. It is still pulsing with enormous energy. So when a supernova explodes, the outer layers of the star are blasted away into space. But the core, the densest part of the very center of the star, can form either a neutron star or a black hole. A neutron star is a very extreme object. It has more mass than the sun, but it's squeezed into a space that's about the size of Manhattan. If you took a cubic centimeter of neutron star material, or about a teaspoon, it would weigh about 100 billion tons here on Earth. And a black hole is even more extreme, of course. It's the densest object in existence. So as I mentioned previously, these really massive explosions are very rare. About 97% of the stars in our galaxy are going to end up as white dwarfs. And as their cores collapse and die, the outer layers of the star more or less serenely, peacefully, calmly float off around them. And this gas is then bombarded by hot ultraviolet radiation from the very hot core in the center. And that gives us some really spectacular fireworks shows. So the image here shows a planetary nebulae that we call the Butterfly. It was taken with a Hubble Space Telescope, and it's heated to over 36,000 degrees Fahrenheit. So imagine that, this super, super hot gas just heated from the center, from this white dwarf that's at the core. Of course, planetary nebulae are a lot less explosive than supernovae, and they're not as energetic, but they're still some of the most beautiful objects in the universe. So this is a gallery here with a collection of planetary nebulae that were observed with the Hubble Space Telescopes. And also the 4 images on the right also incorporate X-ray data, which is shown in pink because X-ray data is not something that our eyes can perceive. So we just added it in a different color to show where the X-rays are concentrated. So whether it ends in a supernova or a planetary nebula, the outer layers of the star will be deposited back into the gas reservoirs of the galaxy. And out of that gas, new stars are eventually going to be born. So the gas that is recycled is enriched, meaning it has more elements that are heavier than hydrogen because of the nuclear fusion inside the star that gas came from. And so every new generation of stars is more and more enriched. Previously, I've talked about black holes and neutron stars. So now I'm going to focus a little bit on white dwarfs, which are pretty awesome in their own right, although they're not nearly as rare as black holes or neutron stars. And this is a quote from Sir Arthur Eddington, who said it best back in 1927, and I quote, "We learn about the stars by receiving and interpreting the messages which their light brings to us. The message of the companion of Sirius, when it was decoded, ran, 'I am composed of material 3,000 times denser than anything you have ever come across. A ton of my material would be a little nugget that you could put in a matchbox. What reply can one make to such a message?' The reply which most of us made in 1914 was, 'Shut up, don't talk nonsense.'" It's just so incredibly mind-blowing. Why are white dwarfs so incredibly mind-blowing? So let me try to explain. For most normal stars, those that are still alive, they're still burning hydrogen in their core. We call these stars the main sequence stars. So you can see them. Yes, you're able to see my You can see my cursor, I can't. That's a bit of a problem. But if you look at the diagonal white ellipse, that incorporates the main sequence. So what I'm showing here is called a Hertzsprung-Russell diagram, or an HR diagram for short. And on the horizontal axis is the surface temperature of the stars. And it's a little unusual because you can see the farther you go to the right, the lower the surface temperature becomes. And then on the vertical axis, you have the brightness. And that's a more conventional scale. The higher up you go, the brighter you get. So generally what you see is that the hottest stars are the brightest, which is what you would expect. That the hotter an object is, the more radiation it gives off. And that is true for the main sequence stars. The coolest stars that are around the mass of the sun are relatively they're relatively cool, they're relatively faint, but the biggest stars, the most massive stars, are also the most bright. But there is an exception. If you look on the lower left corner, that's where the white dwarfs are. And these objects are extremely, extremely hot. However, they are also extremely, extremely faint. And the only way to explain this phenomenon is if you assume that there is a really, really hot object that's just very, very, very small. And that's why the light is escaping at a very low rate, because there just isn't a lot of surface area for it to get, for it to escape through. The other exception to the main sequence is the giant star category, which you can see on the upper right. And those stars are evolved. That means they've run out of hydrogen in their cores and they're close to dying. They might still be burning hydrogen in their outer layer, or they might be burning heavier elements in their cores, but they're not long for this world. So something even more mind-boggling about white dwarfs, and this is important, and I'll come back to it later, is that the more massive they are, the more compressed they become, which is kind of counterintuitive, because generally when we think of a typical everyday objects, the heavier it is, the more mass it has, the more space it's going to take up. But that is not the case with white dwarfs. A white dwarf with the mass of the sun would be compacted to about the size of the Earth. So an obvious consequence is that they're also extremely dense objects. They're not as dense as neutron stars, but still a cubic centimeter or about a teaspoon of white dwarf material would weigh about a ton on Earth. And because of their immense heat, white dwarfs emit a lot of X-rays. They're barely visible in the optical light, the kind of radiation that we're capable of seeing with our eyes. But in X-rays, it's a totally different story. So on the left here, you can see an image that's taken with NASA's Chandra X-ray telescope. And you can see that in the X-ray band, this is an image of the Sirius system. So Sirius A is a very bright star that you can often see in the night sky, even from New York City. It's a very blue star, a very hot star. But it is in fact not an isolated star. It's a binary system. There is another star in that system that is a white dwarf. That's impossible to see with a naked eye. However, when we look at the sky with an X-ray filter, this white dwarf, Sirius B, is actually brighter than Sirius A, which is the star that's still alive. But when we look in the optical filter, you can see the image from the Hubble Space Telescope on the right here. Of course, Sirius A is far, far brighter than the white dwarf, and the white dwarf is barely detectable as a tiny speck. There are a few different types of white dwarfs depending on their composition. And as I mentioned earlier, all stars start off by burning hydrogen into helium in their cores. But what happens when they run out of hydrogen? There will be a period of core collapse, and the star's envelope will expand outwards. This is what we call the red giant phase. Red because it turns cooler, and in astronomy, red is considered lower temperature. And giant because it still has the same mass, but it's greatly expanded. It's just puffed up into a giant ball. But if the star is massive enough, it will then start to burn the helium in the core into carbon. So a lot of white dwarfs are composed mainly of carbon. Now, after the star dies, remember, once the outer layers are blasted off, the white dwarf begins to cool. And as it cools, it crystallizes. And what happens to carbon when it's crystallized under immense temperature and pressure conditions? What? Yes. A diamond. One heck of a diamond, a giant, massive diamond. So if you like diamonds, I hope that it brings you joy to know that the sky might be full of them, huge, gigantic ones floating along in space. An isolated white dwarf will simply continue to cool off and crystallize for the rest of eternity. But oftentimes, stars don't live alone. They're coupled in a binary system. And because white dwarfs are so incredibly dense, they exert enormous gravitational force on their surroundings. So when a white dwarf has a companion star in a very close orbit, it's going to start siphoning off material from that companion, which we're then going to call a donor star. And it's going to just siphon the gas from the donor onto itself. We call these types of binaries cataclysmic variables, because the material is going to pile up onto the surface of the white dwarf, where it's going to get heated to very high temperature until it's going to actually ignite a thermonuclear reaction, meaning it's going to start to fuse hydrogen into helium right there on the surface of the white dwarf. And this will cause a massive explosion, which we call a nova, not to be confused with a supernova, because it's only about 1 million times as bright as the sun, not 5 billion. And novae are so bright that we can sometimes observe them in faraway galaxies. So if you give a white dwarf, which is essentially a dead star, a close companion, it basically can get a second life. But wait, as I mentioned before, white dwarfs have this weird property that the more massive they are, the smaller they get. And you can see it from this diagram on the right here. On the vertical axis, we have the white dwarf radius as a function of the sun's radius. And the horizontal axis shows the mass of the white dwarf. And you can see that the lowest mass white dwarfs have a radius that's about 4% of the sun's size. But the more massive the white dwarf becomes, the more its radius shrinks. So it follows from that, as the late great Chandrasekhar discovered back in the 1930s, that there is a limit to how massive a white dwarf can be, because there must come a point where it becomes so compressed that it can no longer survive. And he was right. So this critical mass, which is known as the Chandrasekhar mass, if this is exceeded, and this can happen either if two white dwarfs that orbit each other merge, or if the white dwarf in a cataclysmic variable accumulates a lot of extra material that's siphoned from the donor, then the white dwarf will implode in a type 2 supernova, which can give birth to a black hole or a neutron. Sorry, which will not give birth to a black hole or a neutron star, unlike a type 2 supernova. So type 1a supernovae, which happen when a white dwarf exceeds the Chandrasekhar mass, are completely destructive. They destroy the white dwarf fully. There is nothing left afterwards. Now, going back to black holes, you might wonder, if no light can escape from a black hole, how do we know that they're there? How can we see them? And there are actually several answers to that question. But first, a reminder that binary star systems are found throughout the Milky Way and other galaxies. Most stars, especially the very massive ones, don't live alone. They have companions. So when a black hole or a neutron star has a close enough companion, then the compact object, the black hole or neutron star, is going to start to cannibalize the donor by siphoning off its mass. Now, this material is going to form an accretion disk of hot gas that swirls around the compact object. And accretion generally means that there's going to be a lot of very energetic X-ray emission. And therefore, black holes are some of the brightest X-ray sources in our galaxy. So one answer to the question, how do you find a black hole? You look for the X-rays that it gives off. But there's another way too. So in the case of a black hole binary system, where the separation between the black hole and the other star is small enough, we can find the black hole by looking for the bright energetic X-rays coming from the heated plasma around the black hole. But when the separation is too big for the mass transfer, we can sometimes detect the black hole by measuring the orbit of the companion star around it, since the companion star does emit a lot of light. So by tracking the motion of the companion, we can determine the mass of the dark object that it's orbiting around, even if we're not able to observe the black hole directly. And a similar method was used to actually measure the mass of the supermassive black hole at the center of our galaxy. And I'm sorry, but I'm not able to speed up this video. But this is, so Nobel Prize winner Andrea Ghez did this over the course of 20 years. She tracked the orbits of massive stars around Sagittarius star, the supermassive black hole. And from there, she was able to indirectly determine what the mass is. And she was able to determine that it's actually a 4 million solar mass object at the center. And this is just a cartoon that's trying to illustrate how you see these different orbits of the stars around the black hole. And with that, I'm going to wrap up my talk. I want to thank you again for coming. And I also want to thank Amanda, who's our outreach coordinator, for organizing the event, and my advisors, Chuck Haley, Kaya Mori, and Mike Shara, and the NSF, and my kids and my cat, who have emotionally supported me to varying degrees. Thank you again for being here. I'll take questions.
Okay, thank you so much. We're now going to have a Q&A. So you're welcome to raise your hand to ask a question, but if you feel more comfortable typing it, we have a Google form that is open. You can go to the link or take a QR code. I'll be repeating the questions that you say just to make sure that everybody in the room and the folks watching on YouTube can hear. But otherwise, Shifra will be the one answering them. Yes.
On previous slides that we talked about there was like on the graph it said Fermi gas, and I was wondering what that was.
Oh, okay, so the question is about Fermi gas on one of the diagrams that Shifra showed.
Right. So electrons are fermions. So the rules vary depending on what kind of material you have. Because electrons are fermions, there's something called the Pauli exclusion principle that applies to them. And the Pauli exclusion principle essentially says, if you have a system, you can't have two particles in that system be in the exact same state at any given time. And that comes into play when you limit what the size of the white dwarf can be, how small it can get, because there comes a point where you just can't squeeze in any more of them.
Why do cosmic voids exist?
So this is not my area of expertise, but I will try to answer as best as I can. So in the very, very early universe, the density of matter was almost the same everywhere, but there were small fluctuations, tiny, tiny differences. And as the universe expanded, those tiny differences became big differences. And that's why we have areas that you might call cosmic voids, where we don't see a lot of matter, and other areas with big concentrations of matter. Does that make sense? Great question.
In the front? Okay, question
Definitely.
was, can a black hole suck up a rocket if it gets too close?
Yes, it would have to get very close. If the rocket stays far, far away, the rocket is going to be perfectly safe. But if you go past a point where the space-time is really, really distorted and really twisted up, then it's not going to be able to escape.
Okay, we're going to do one from online. Does dark matter emit X-rays?
Okay, great question. Dark matter doesn't directly emit any light in any waveband, including X-rays. Hence, it's dark matter. However, when dark matter annihilates, meaning it's basically broken down into something else, then there may be X-ray signatures. It depends on the type of particle and the type of process that's going to determine what kind of energy that radiation is going to have. But the short answer is yes, probably.
Okay, see one question in the back. So why do we see black holes in the center of galaxies?
That is an excellent question. So firstly, I want to point out that we don't really have a very good understanding of how these really supermassive black holes form. We have some theories, but we have some hypotheses, actually, that would be more accurate. But we don't really, we're not really sure how they happen because they are so very massive. However, if you think about a galaxy, generally, the closer you get to the center, the more concentrated the matter is. The closer the stars are to each other, the more dense the material is. So it would make sense that the very densest part of that galaxy is in the very center. And maybe it's a little bit of a chicken and egg problem, because if you start off with a supermassive black hole, that exerts an immense gravitational pull, and that's going to draw other material in. It's going to draw other stars in, and so on.
Okay, one question in the back. Great. So how do we know how far away black holes are if they aren't giving off any light and we can't shine a laser on them?
Very good question. Sometimes we don't actually know. Sometimes we have a range. We can say it's, somewhere between 10,000 and 20,000 light years away. We're not really sure beyond that. But there are different signatures. We look for signals in the radiation, for example, the X-ray radiation. We look for signals that tell us how far this light traveled before it got here. And so sometimes there are clues that can help us figure that out.
I'm going to ask one from online. What is a singularity?
A singularity is a point in space-time that's essentially of infinite density and no value. So it's a single point. It's just so incredibly dense that it sort of folds space-time all around it. It's not something that's really intuitive, but it's something that we can try to conceptualize.
Okay, one more on the form. Since Sirius B is a dwarf star, will it eventually end up impacting Sirius A?
Excellent question. Probably not. So I mentioned cataclysmic variables. These are star systems where there's a white dwarf and a companion star, and the white dwarf is siphoning off material from the companion. But the distance between Sirius A and Sirius B is big enough, even though they're orbiting each other, that's unlikely to happen, certainly for many billions of years. I don't think that's expected to happen. They don't interact in that way.
So the question is, do we know what happens or have we observed when a black hole dies?
That would depend on what you mean by black hole dies. So in principle, black holes they're already dead. So there's nothing dynamic necessarily happening on the inside. Well, we don't really know, do we? Because we can't see inside the event horizon. So we know that it's gobbling up loads of material from around it, but it'll just keep going. It'll keep doing that, into perpetuity. But there is such a thing as Hawking radiation, which is essentially a black hole leaking particles at the event horizon. And the way that happens is that you have particles that break up into matter-antimatter pairs, and sometimes one half, before it has a chance to recombine, one of them will escape the event horizon, the other will fall back into the black hole. So technically, it is possible for black holes to evaporate over time, but your typical garden variety black hole is going to take virtually an eternity to completely evaporate.
Okay.
What do you study?
What is Shifra study?
I'm an observational X-ray astrophysicist. So I love black holes. I study a lot of black holes, but also other accreting, what we call compact objects. So all kinds of dead stars, neutron stars, white dwarfs that are basically cannibalizing their companions. Their zombies come back to life, and they're extremely energetic, which is why I find them very exciting.
Okay, I'm going to do a couple from the form. You mentioned that a black hole is neutral. Does our sun have a charge? And if so, what?
Ooh, I don't actually know that one. Great question. Ooh, does anyone here know? No? I don't know. I'm not an expert on the sun. It's still very much alive, so.
Chuck, do you know? So the sun has a very small charge. Okay. How big was the star that formed the black hole in the center of our galaxy?
Great question. So if you think about the black hole at the center of our galaxy, like I mentioned, it has the combined mass of about 4 million suns. Now, part of that mass could have been accumulated over billions of years, but it had to have started out already very massive. So we think that supermassive black holes aren't formed through the typical formation channels. And there are different theories as to how they are seeded, which is what we call when, the early stages of a supermassive black hole. And there are competing theories as to how that comes about.
Okay, question? Do black holes have a limit to growth?
Interesting question. I think mostly the limit is going to be related to how much it can gobble up. So if a black hole is in a region of space where it's already gobbled up all the gas around it and there's nothing else around, then it'll stop growing.
This might be, what your opinion question or like fashion question, but, like, is a black hole more of a place or is it an object? Because you think people like fall into it, there's like the singularity is reach, but then again, it is like what a star turns into.
So is a black hole more of a place or an object?
I think that's a fascinating philosophical question. I'm not sure how to think about that because, like I said, a singularity, it's a point in time. It has no volume. So it's hard to think of it as a place, but there's certainly an event horizon, and that's definitely a place. Yeah, I'm not sure. It's a very interesting question. Never thought about it that way before.
Okay. We had another question in the front. If you still do, go for it. We are really concerned about this rocket. How close can a rocket get without being sucked up to the black hole?
Yes, very good question. So it's going to depend on the black hole. So I already mentioned that every black hole has an event horizon. So the radius, how far where that event horizon is going to be depending on two things. It's going to depend on how massive, well, actually, no, sorry. The event horizon is going to depend on the mass of the star. However, how close you can get without getting sucked in, that's going to depend on the mass of the black hole, but it's also going to depend on the mass of a spin. Sorry, on the amount of spin. So if you have a black hole that's spinning really fast, like a top, then you can get closer to it and still be in what we call a stable orbit without actually getting sucked in. So there's something we call the innermost stable circular orbit. It's a real mouthful. We say ISCO for short. And that is the orbit that lets you actually, you know, go to the black hole with a rocket and then escape again without getting sucked in. So that's going to vary depending on a more massive black hole is going to have a bigger ISCO, but also a black hole that spins faster is going to have a smaller ISCO. So those two things are going to affect what that is.
Okay. Question?
Oh, okay. Now you're getting into the interesting stuff. Sorry.
That's okay. So how do you determine the spin and the direction of the spin of the black hole and how fast?
So like I mentioned, the faster a black hole spins, the smaller that inner radius is. That means that if you have a black hole with an accretion disk around it, the faster the black hole spins, the closer the inner part of the accretion disk is going to be to the black hole. That means the more distorted the signal is going to get. So that's actually one of my favorite things to do, is to look at the spectrum from a black hole and try to figure out, is this signal, is this radiation distorted by the gravity from the black hole? And that kind of helps us constrain, okay, then how distorted is it? How fast is this black hole spinning?
So what then causes or influences the spin of it?
So what causes or influences the spin of the black hole?
Very good question. So like I said, most objects in the universe spin. So the black hole formed out of a massive star that collapsed. Before collapsing, that star was spinning. Now, the core of the star collapsed into a tiny, tiny point. So by conservation of angular momentum, because it's now really, really small, it has to spin so much faster in order for angular momentum to be conserved, because angular momentum is basically the rotation and also the mass. So because it's now, sorry, well, it's the rotation, the mass, but also the radius, the size of the object. So because the black hole is now tiny, whereas before it was huge, it has to spin faster to make up for that change in size.
Okay, we're going to take maybe 5 more questions, please. So how do we learn about black holes and model them when we can't create one?
Through imagination, also called theory. So as I said, Chandrasekhar was the first person to realize back in 1935 that there's a limit to how massive a white dwarf can be. So then they postulated, well, if it, oh, I'm so sorry. I think it's mine. No, it's not mine. Sounds like mine. So they postulated, well, if it can't be a white dwarf because it's too massive to be a white dwarf, obviously it has to be something else. And that something else is either a neutron star or a black hole. Sorry, what was the question?
How do we model them?
How do we model
Yes.
them? Yes. So essentially starting from the principles of general relativity, thinking about what happens. So general relativity essentially tells you how does mass curve space-time? How does mass affect the space around it? And so when you get an object that's extremely massive, but also extremely compact, general relativity helps you figure out. So it's essentially a theoretical.
So as an observational how do you access the Earth-based or space-based telescopes and most of your work based on observations that are made by others, or do you actually, in your research, get access to some of those?
So how does an observational astronomer get access to either Earth or space-based telescopes? And then for Shifra, where does most of her data come from?
It's a mixture of, well, so I'm a high energy astrophysicist, meaning I look mostly at X-ray sources. And because our atmosphere protects us from X-rays, thank goodness, because otherwise we'd be a soup of plasma, we have to put our X-ray observatories into space. So most of my data comes from space. And it's a mixture of proprietary data, which I applied for. I had an idea and I asked them, can you observe this object so that I can study it? And other observations that other people did, for their own nefarious purposes that I can just use and adopt for my own work.
Okay, we keep having questions, but we're gonna run out of time. So maybe these two folks haven't asked a question, so more in the back first. Yeah, so can you destroy a black hole maybe by trying to change its charge? So feeding it a lot of protons.
I don't see how, but I'm not sure, actually. I don't think so, but I would ask someone with, Chuck, do you want to weigh in here? Sorry. The question was whether you can destroy a black hole by making it electrically charged.
So, yep, you can never get rid of a black hole. We're all made of things like protons, and black holes don't care when they're gobbling us up. But as we've learned, we're not getting too close, so we're okay. All right, last question. Yeah, so why did Shifra get into astronomy, and any advice for younger folks?
Yeah, that's sorry, I did not grow up wanting to be an astronomer. I didn't know anything about astronomy growing up, but once I started to learn, the first time I started learning about astrophysics, it was just the coolest thing that I'd ever heard about, and I wanted in. And what advice do I have? I think it's not for the faint of heart, but if you're passionate about this, then go for it and give it your everything.
All right, and I think I'll end with a philosophical one that someone submitted on the forum. If a black hole eats, spins, and emits gas, can you really call it dead? So we'll end there. Shifra, if you'll change the slide and turn off the microphone so I can come back over there. We're now going to do the raffle, which I'm sure is why you are all here. Can't go closer yet. Is that? Yeah. Okay, so how we're going to do this is you are all sitting in a chair that has a seat number. So if you'll turn around and look at your seat number. All right, so the way we're going to do this is I'll alternate if this is your seat or an empty one that is directly to your left. So everybody practice left and right. This side, G12. Do we have anybody in G12 or directly to your left? No, all right, we'll do a different random one. All right. K18, directly to your right this time, or someone sitting in it. Okay, we're gonna go faster. M8. You're in it or it's to your left. All right, none of us should play the lottery. This is what I'm learning. E17. Woo! We have our first winner. All right, you win a mug that is fresh from the box, so please wash it. Inside is also a sticker. Okay, A5, directly to your left or your seat. So close. G3, to your right. All right, you also win a mug. E15. All right. We know who should be playing the lottery. And our last prize for tonight, N12. Any? All right, and we have a tote bag. If you'll raise your hand again, E12. All right, I have been consulting with the meteorologists upstairs, and they tell me the forecast is okay. So what that means is there is a telescope outside of Pupin, but I want you to have low expectations because there are still clouds. So if you go, we're on the 3rd floor right now. And so if you go up to the 5th, either by stair or by elevator, there is a telescope that is looking at the moon. When a cloud is not over the moon, we have a good view. If there is a cloud, we don't have a good view. So before you all leave, I just want to say thank you for coming and thank you to our wonderful speaker again. As you might be aware, Congress is deliberating on its budget. If you have opinions about how much science should be funded, please reach out to your representative. There is a QR code here. When the projector is clear, that would bring you to your representatives if you want to share your opinions with them. Thank you so much. Have a good night.